In this problem, we are presented with x of s, so that is the Laplace transform of x of t is x of s, and we want to know what's happening in the time domain at time is 0 and at steady state. So when I'm calling it x of infinity, but after a long time, what's the value of x? So we want to know these two values about x in its time domain, and right now we are in the frequency domain. So in this example, we are skipping over the step where we would have gotten to this x of s by taking some Laplace transform, and we're going to start already in the Laplace transform state of this. Now, one way we could solve for x of 0 and x of infinity, or the steady state value, is we could simply solve for x of t, put in t is 0, put in a large value for t and see what x is, and that would tell us our answer. But in this case, because we're talking about initial value theorem, final value theorem, I am not going to solve for x of t. I am not going to do an inverse Laplace transform, yet be able to solve for x of 0, or x of t equals 0, and x as t goes to infinity. So in order to apply IVT, FVT, I need to actually look at what is happening to s times x of s. So let's actually start there. Now notice I have x of s here in its kind of pure quadratic form in the denominator, and I have it factored already. Both of these forms are going to be useful for what we're going to do next. So I just kind of pre-factored it since this is factorable. And we've actually already looked at this problem and already solved this problem previously. So we already know what the answers should be, and we can refer back to that for some verification. So what's s times x of s? Because we're going to need this actually for our next parts. So that's going to be s over s plus 2 times s plus 3 is one way we can express it. Now, before I apply IVT and FVT, I need to know what are the poles of, remember, s times x of s. If all of the poles are in the left half plane, then we can apply initial value theorem, final value theorem. So that's what we need to check first. So what are the poles of s times x of s? Well, I've just written s times x of s. The poles are going to be the values of s that make the denominator 0. And when it's in factored form like this, that's really easy to find, because we know that -2 is going to be one of the poles, and -3 is going to be another. Because if we put s equals -2, well, we have 0 times s plus 3, that's 0. If I have s equals -3, I have -3 plus 3 is 0, times the s plus 2, that's also 0. So these are the exactly two poles of s times x of s, and when we look at them, are they in the left half plane? Yes, they turn out to be purely real, but all that really matters for left half plane are the real parts negative, strictly less than 0. And in this case, yes, both poles are in the left half plane. So now initial value theorem can be used, final value theorem can be used. So the order we solve this in doesn't really matter. Let's start with x of 0. So we need, what is x of 0? Well, we can use initial value theorem to figure that out. This x of s is eligible because s times x of s has poles strictly in the left half plane. So x of 0 is the same as the limit as s goes to infinity of s times x of s. Now I can put in the value for s times x of s. So again, limit as s goes to infinity. And this is where we want to pay attention. It's s times x of s. So it's s over, and in this case, because I'm doing the going to infinity, I'll have s over, I'll do s squared plus 5s plus 6. I think the unfactored form is going to be a little bit easier to work with when we are taking the limit as s goes to infinity, as we'll see in a second. All right, so we have a fraction where the numerator is of degree 1 and the denominator is of degree 2, and we're taking the limit as s goes to infinity. So if you remember back to your calculus or pre-calculus class, when we have polynomial numerator, polynomial denominator, the variable is going to infinity. The rule here is going to be when the denominator is of a higher degree than the numerator, then always this is going to go to 0. And it's a different rule for when the numerator and the denominator have the same degree or when the numerator has a higher degree. But in this case, the denominator's degree is higher. It's going to go to 0. And again, we did already find the closed form solution to this previously, so we will be able to verify this. All right, so initially, x of 0 is 0. Now, what happens to x of infinity, which I'm usually going to call, I'll put this SS here for steady state. They're going to mean the same thing. After enough time passes, what is the constant value to which our variable is going to go? So x infinity or x steady state. And for that, I want to use Final Value Theorem. Again, the poles of x of s are all in the left half plane. So just as I was allowed to use Initial Value Theorem, I can also use Final Value Theorem. So x steady state will be the limit as s goes to 0 of s times x of s. So that's the limit as s goes to 0 of. Now I'm going to use the factored form this time, but it's still that x times x of s. So I copy down the s over s plus 2 over s plus 3. So in this case, I can take the limit directly in that I can just make s equal to 0, because doing so does not make the denominator 0. If it did, then I would have a problem when I'm taking this limit. But here, that's not going to be a problem. If s were -2 or -3, we would have a problem, but 0 is actually fine. So if we do that, the numerator actually is going to be 0. And then in the denominator, we're going to have 2 and 3, because I have 0 plus 2 times 0 plus 3. But in the end, it's actually not going to matter. Because the numerator is 0, I get a 0 here as well. So it turns out this one is not terribly interesting in that it starts at 0 and ends at 0. And again, we have the closed form solution. We've plotted the closed form solution previously. We can look at that for verification. It starts and ends at 0 according to Initial Value Theorem, Final Value Theorem. Now, what happens in between? This doesn't tell us any of that. It doesn't tell us the maximum. It doesn't tell us if it's positive or negative, in fact, just that it starts at 0 and eventually ends up back at 0. But we were able to get this information without doing an inverse Laplace transform. All the analysis was done in the frequency domain by taking the limit as s went to infinity of s times x, and then the limit as s went to 0 of s times x of s. All right, so again, remember here when we're applying initial value, final value theorem, the poles are going to be of s times x of s, and then the limits are also s times x of s. It's very easy to forget that we are multiplying the x of s term by s, and that is actually what we are evaluating the poles of and what we are taking the limits of.